Hi, I'm Harish, and today we'll be looking at the Taichi parallel programming language. So, this is a brief summary of what we'll be covering today. So, we'll start off with a bit of a background. So, what exactly is the problem that we're trying to solve? Then we'll go into what exactly is Taichi. Then we look a bit about how it works, so how to actually write a Taichi program. Then we would demo a simple matrix multiply program written in Taichi and compare it to the OpenMP implementation of it. And then we look at some common use cases. So what can you actually use Taichi for, as well as how it's currently being used in the real world. All right, so let's start off with a bit of background. So a lot of high performance computing applications are typically written in C++ or CUDA. These are obviously very powerful languages, but even though they are powerful, they can be quite hard to actually develop with, especially because there can be a lot of complexity in terms of actually writing the code for it as well as debugging certain things. So you'd have to worry a lot about, how to manage memory with these languages and just have to deal with, debugging segmentation faults and a lot of other memory errors that you can get. So because of this, it can take up a lot of development time to actually write these programs, and we notice a lot of the time that it can end up in a scenario where we're often being bogged down by all these language details. And on top of that, even if you do get the program right and it works well, even re-implementing a certain program with a new algorithm and just refactoring the code, that also does add a bit more complexity as well. And then since it is quite hard to develop with, then actually refactoring the code can be a non-trivial task. So this is where Taichi comes in. So Taichi serves to be this simple parallel programming language that makes development quite easy, as well as just overall just reduces the barrier to entry to write these parallel programs. And it's almost this simpler alternative to CUDA. So it was developed by MIT in 2019 by the CCL lab there. And essentially, it was initially developed for computer graphics researchers to serve as this really easy way to write these parallel programs. So what it is almost embedded and built on top of Python, and we get in we later on we'll get more into how to actually integrate Taichi into Python. But essentially, what it does is it uses some kind of JIT compilation to generate the code once you enter this certain Taichi entry point. And obviously, this compiled code is highly optimized, and another thing Taichi does is it uses this sort of S-node tree structure to actually represent certain data. And because of that, you can support dense and sparse matrices quite easily. It also provides support for these quantized data types that are customizable. So especially floats, we can actually customize, okay, how many bits we're going to use for the exponent and the fraction. And this just allows us to make the data more compact, especially when we don't need to use that many bits. So it allows us to pack more data into a memory unit, and we know that memory can often be a bottleneck in some applications. So this is of course very useful. It also has this thing called the ahead of time mode, and this pretty much does some kind of compilation step, and it allows Taichi to actually be used across different platforms. Anyway, in the right, you can see a performance analysis of Taichi. So this is a graph obviously shown by the researchers of Taichi and what they've shown on their GitHub. And we can see that essentially Taichi is, uh, compared to CUDA, it is performing reasonably well, and it is outperforming CUDA on a few benchmarks as well, such as the MPM. It is significantly outperforming CUDA, and there are many benchmarks where Taichi either outperforms CUDA or it actually provides a pretty much comparable performance outcome. But you can see that in things such as the N-body simulation, what we can see is CUDA does outperform Taichi. So there are obviously cases where CUDA does perform better, but we can see that Taichi is a reasonable alternative according to the performance graphs that have been shown. All right, so how it works is very simple. So we have almost this basic Python program, and it's almost downloaded as this library. So the first thing you need to do is obviously just specify a device. So you would want to say, okay, I want to run this on the CPU or GPU. And then we use a function decorator in Python where we can say, so we define a kernel point. So at ti.kernel, we can define a function to be a kernel, and then we can define another thing to be a Taichi function. So the kernel is the main entry point into Taichi. So this is where Taichi actually takes over the runtime. And functions can be callable within kernel. So it can be called by a kernel or it can be called by another function within a kernel. And this is essentially how it works. Another thing to note is this uh, type annotation you see here is essentially pretty much required when you have a kernel. So all kernels must have this type annotation in the function. And in terms of representing certain data in Taichi, we see that the common thing is to use fields. So we can have, there are many different ways to define a field. So we have scalar fields, matrix fields, vector fields, and struct fields. So they essentially boil down to the same thing where we have this kind of uh, almost this array structure. So here we have almost a 2D array structure. So what it's actually storing is here it's storing in this case it's storing a float, so a scalar value, and here it's storing a matrix value. So here it's storing a 2 by 3 matrix. Then we can have it store uh, an array basically. So an array of length n. So this is defined as a vector field. So I guess this makes sense because you're trying to say, okay, we'd access something and then it has like some kind of vector in like the XYZ direction or something like that. And here we have a struct field, so we can include even more information and kind of specify it more explicitly. And then we have fields that are more advanced. So this is a very important part of Taichi. And as you can see, this kind of goes into how Taichi uses this S-node structure. So in the bottom right, we can see two ways to define the same thing. So here we are essentially kind of leveraging this S-node structure and we are defining this 3 by 4 matrix, but it only has one layer beneath the root, and here it has two layers beneath the root. And how this is useful is you can use this to actually just define how we kind of access data using I and J, and how we can use this to actually kind of what we can do is we can use this to exploit certain access patterns of the data. So as you can see here in this program over here, we are accessing X and Y in different ways using I and J, right? So X is being accessed in a row major way and Y is being accessed in a column major way. And what we can do is we can define the S-node structure to be structured in a way that exploits this access pattern. So as you can see here, we are defining X in a row major way because we are defining I, and then we are defining J underneath I. So that's how we kind of access I and J. Whereas here we are defining J and then I underneath J. So this helps kind of exploit this S node structure. And furthermore, we have a different example, and this is an example that Taichi has given in their website as well. So essentially, this is to kind of function as, let's say we have some kind of image matrix and we are accessing it in kind of segments of 8 by 8 blocks, right? And what we can do is we can define it in as a flat field, but we can also define it as a hierarchical field. So we define kind of like almost this index into all these blocks. And then within those blocks, right, those each block stores this 8 by 8 matrix that of the image. So this kind of also exploits this kind of access pattern. So now let's go into a demo of Taichi programs. So first of all, let's just run a regular implementation of a matrix multiply operation return uh, that's done in Python. So here we have essentially the square matrix that we define with random values, and then we multiply it with itself, and we kind of collect the result. So we can see that the regular implementation runs in 0.81 seconds, and the Taichi implementation runs in 0.029 seconds. So here we can see how we are defining this kernel function with our matrix multiply. And then we have an OpenMP version that is doing very much the same thing. So let's just recompile it and then let's run it. And this is running at 0.021 seconds. So we can see that Taichi is definitely outperforming uh, the regular implementation of Python, which makes sense because it's parallelized and optimized as well. However, in this particular instance where we ran it, it's actually trailing behind the OpenMP implementation. All right, so getting back into what we were discussing about Taichi. So first of all, what are some common use cases? So I would say the common use cases are essentially the use cases of any parallel programming language. So one thing is you can use it in these kind of interesting math visualizations. So here we have a Mandelbrot simulation, and then we can obviously use it in machine learning where we're doing a lot of matrix multiply operations and calculations like that. In the top right, we can see we can be used in kind of graphics rendering, and here we have a light source, so it's also implementing some ray tracing algorithm. It can also be used in robotics, and you can use it for things like SLAM and applications like that. And then we can also use it to actually conduct kind of fluid simulations. So this kind of plays into how it's good at, managing these physics simulations and just general drawing pixels and voxel art. Uh, that is something that Taichi can do as well. So these are some common use cases that you can use it for. But how is it being used in the real world right now? So it hasn't taken off a lot. Like it hasn't like really taken off, but it is a reasonably recent programming language. And how it's currently being used is in ETH Zurich, they use it in their physics simulation course. So a lot of students have used it to actually implement these physics simulations. And then there's this uh, video editing and generation platform called Kuaishu, and this uses it to kind of generate special effects for videos. So obviously these special effects can rely on certain physics simulations. So Taichi is pretty good at uh, calculating and conducting those simulations. So it's a useful language for that. And then Oppo is using it for their wallpaper background. So if you want a interactive background that kind of uses physics simulations for particular effects, uh, Oppo kind of implements this in Taichi. And that is it. Thank you so much for listening.